Good morning. Welcome to Krishna's classroom. We continue with our exploration of the concept of determinants. In this context, we looked at the 2 by 2 determinants earlier, and we are, for the sake of developing the notations to deal with the general case, working on 3 by 3 determinants, because where computation is simple, at the same time we can show how the new the notations have to be reworked so that we get an easy transition to the case N. And this is probably redundant. I mean, this working on R3 is redundant. I know that it's just overdoing it, but perhaps for the students it's a study to understand how ideas are explored and generalizations are arrived at. So the sole purpose of doing this, otherwise I can straight away go to n dimensional spaces and work with it, but that is not that's not what I want to do. I want to deliberately do it for the case 3 also, because 2 is too trivial or too simple to be to know the complexities. But when it comes to 3, possibly it is slightly more complicated. So we will work with 3 and get a feeling for how the generalization can be carried out. Get a feeling for get the right kind of notations to carry out this. So what we did last time was to look at what are called 3 linear forms on R3. By which I mean, see, you have got R3 direct sum, R3 direct sum, R3, and then we have maps defined from there to R with the property that they are linear in every one of the variables with others held fixed. So this is what we mean by a 3 linear form. And then we found that the 3 linear forms form a vector space, and we also constructed a basis for that, and we found that it's a 27 dimensional vector space, that is 3 to the power 3 dimensional vector space. Now what we want to look at is the alternating 3 linear forms on R3. That means a subclass of these 3 linear forms with a specific property, so that, of course, and you see that they form a vector space again, a subspace of the space of 3 linear forms. And we want to fix a dimension of this space, and that's our objective. So we start with the definition. It's a continuation of what we did last time. Definition: a 3 linear form A on is said to be alternating, and alternating an alternating three linear form. If A of x1, x2, x3, xi belonging to R3 changes its sign with the interchange of any pair of the variables keeping the other fixed and keeping the magnitude that means the value of this changes sign. Consequently, we have the following, that is A equal to minus A equal to minus A equal to minus A and that's equal to A x2 x3 x1 that's equal to A x3 x2. Now these are the relations. So between A x1 x2 x3 and A x2 x1 x3, the x1 and x2 has been interchanged. X3 can be kept the same, fixed. Then what it says is that these two maps have the same value but with the opposite sign. There is one interchange of a pair of arguments have been interchanged. Similarly, here the x2 and x3 has been interchanged. x2 and here x3 and x1 have been interchanged. Therefore, there is a change in sign, but the magnitude remains the same. On the other hand, in this case, you see that there is a two interchanges that goes on. So, each time when you interchange it, a sign changes, therefore, you get a positive sign. For instance, to go to x2, x3, x1, from x1, x2, x3, you can do it in several ways. So, you can you want to bring x2 here, so interchange x2 with x1. So, a sign change takes place. Then from there, so x1 comes here, and then you take so x2 comes here, and then you interchange x1 and x3. Okay. So, what one does is x2, x1, then x1 and x3, you will get a, x2, x3, x1. So, two interchanges are taking place. Therefore, the sign remains the same. And similarly here, you know, the x1 and first interchange x1 and x2, okay. First interchange x1 and x3, and then interchange x2 and x1. So, that will give you the same sign. So, there are two interchanges taking place, or what you call two transpositions taking place. So, here there is only one transposition, here there are two transpositions. So, this is the entire thing that you can list out. When you have finitely, when you have n is small, you can easily list it out. Okay. Now, this is true for every choice of x1, x2, x3 in R3. So, that defines what is called an alternating three linear form. Now, one of the things that you observe is that one easily observes that sum of two alternating three linear forms is again an alternating linear three linear form. Similarly, scalar multiple of a three linear alternating form is again a three linear alternating form. Therefore, what happens is that it becomes the collection of all alternating three linear forms form a subspace of the vector space of all three linear forms. Okay. Now, we make some remarks. One, the collection of a subspace of the collection of three linear forms on R3. This is trivial. And the second statement is this: if any two of an alternating linear form is identical, same, then the is the zero form. Not the zero form, then the it is 0. That is, what we want to say is this: if you have xi equal to 0 whenever I equal to j or j equal to k or I equal to k. That means if any two pairs are identical, that is xi equal to xj or xi equal to xk or xj equal to xk. In all these situations, a of xi, xj, xk equal to 0. Now this is quite easy to prove because you take a of x, y. This is also equal to minus of a of x, x, y. The reason is if you interchange this is alternating, therefore the magnitude remains the same but the sign changes. Okay. The consequence is that, which implies similarly the other two situations when j equal to k and I equal to k. Okay. So this is quite straightforward and this information is useful. Now we want to explore, therefore we have seen that it's a vector space and therefore we want to explore this vector space further. Okay, we will use a notation also for this. So let us write this for notation. The subspace of all alternating A3. What you can put out there. Okay, so let us choose this notation for the sake of developing this talk. Now, the question that you ask is, you know that this is a vector space, it's a subspace. What is the dimension of Now this is a natural question that you immediately ask and which is required for our analysis. So what we do is we try to construct a basis for this. Okay. Now what we do is, you know that any okay, let us take, so we have the following theorem. Now we have, let us recall this. Now you see that we have defined three linear forms E1 EI cross EJ EK by EI cross EJ cross EK of acting over EL EM En equal to delta IL delta JM delta now this defines the, now you know that E1, E2, E3 are the standard basis for this definition we have made. Now you see that you look at the collection of all these EI, EJ, EI cross EJ cross EK we have defined, and we look at the entire collection of this, and what we have proved is that this is a basis for forms a basis for the space of all forms a basis for space of all that means there are 27 elements in this, therefore the dimension of this space is equal to 27. Now let us, so you know that, so what you know is that, so let A be an alternating and linear form. It's an alternating three linear form. We know it's a vector space, therefore let us explore what kind of vector is A. Now you know that A can be written as the following, that is sigma ijk 1 to 3 A now you can easily see that aijk is equal to A evaluated at EK. Therefore, you have this representation already available. This is a unique representation for A. Now let us, this is for any three linear form. Now let us use the fact that A is alternating. Since A is alternating, what we have is these properties are there. A of equal to A of x1, x3, x2. This is equal to minus A of x2 which is equal to minus of, which is equal to A of x2, x1, x2, x3, x1. Now which is also equal to A of x3 x1, and this is equal to minus of, sorry, plus of A of now these are the relations that you have. So let us use this. So if we use this, now what you get is the following. Now you see that whenever EI equal to EJ or EJ equal to EK or EI equal to EK, you know the corresponding coefficient vanishes because this is A is alternating. Okay. So note A of EI zero This property let us make use of, and then that brings in lot of reduction, because a, I, j, k, whenever the indices, a pair of indices repeat, it is going to be 0. So this reduces a to the following. For the first stage we can apply this, and then we can apply the other one. So what you get would be the following. This is equal to, so at the first stage this is what you get. A is equal to consider all the 27 terms, this is what you get. A equal to this is equal to minus only 6 of these terms will survive. Minus E2 E3 of plus A of E2 E1 of E1 minus A of E3 E1. How does this come? Keep E2 the same and interchange E1 and E3, and then you have the term A E1 E2 this is what you get. So A turns out to be this. But then again we have not completely exploited the alternating nature of A. Further, we have the following information. Now we have this kind of relation with E1, E2, E3, and then make use of that. So if you make use of that, because they are all related, they are all connected with A, E1, E2, E3. Okay. So if you use that, this is what you end up with. Therefore, this is equal to I think what I can, no, this is actually this, because I have not changed the sign. Okay, this is it. Now we make use of the fact that how A, E1, E2, E3 is connected to all these. Then you end up with the following. That is, you can write this as A into, there will be changes in the sign, and you end up with E1 E3 minus E2, or rather minus E2 cross E3 plus okay, plus third term, you end up with E1, then minus what next? You have E3, E2, E1. So, okay, E3 plus you have E3, E1, E2. So it is 2 here. So you see, it is a scalar multiple of a single alternating form, and this is a scalar. So given E1, E2, E3, you can compute this. Therefore, I can write this as some constant into so any A belonging to script A, okay, is a scalar multiple of a single 3 linear alternating form. That's what we have proved, which is not equal to 0. Hence, it's a scalar multiple of non-zero three linear form. D non-zero form. You can write down what it is. E1 cross E3 minus E1 cross E3 into minus E2 cross plus what's it? B1 minus so this is non-zero alternating three linear form. Okay. So every alternating three linear form is a multiple of a scalar multiple of this, and the scalar multiplying scalar is the value of A at E1, E2, E3. Okay, so that's what we have proved. That is now you see this is non-zero, that is very clear, because if you operate this on E1, E2, E3, then this all other terms, the operation of that will give you 1 there, and similarly you can work on other places. So certainly it's a non-zero three linear form. So that's a very interesting information. So we have got this space one dimensional. Okay, now we want to explore the so what exactly is this? This is what we want. So we want to make use of this to understand the structural concept of determinant of a linear operator on Rth. So now let us write with respect to the basis E1, E2, E3 for R3. Let us assume that A is represented by the matrix where Aij's are real numbers. Okay, this is a unique representation that you have with respect to the basis, the ordered basis. Now I want to make a remark here, because it may appear when we explore the determinant, it may appear as though we are working with a specific representation for A. Okay, but that is not really true, because if you were to use any ordered basis and write down the corresponding matrix representation, you see that they are connected, the two different representations are connected through a similarity transformation, that we know. and the consequence is that if A prime represents the matrix representation of A with respect to some other ordered basis, then you see that the determinant of A is going to be equal to determinant of A prime. So the determinant is essentially an invariant associated with A. So that we shall have, and we have the standard definition of the determinants. So let me not bother about that, we will come to it when we make the remark. Now let us make an observation. Suppose A belongs to R3. Let any vectors in R3. Now what is given is that A x1 real number, A is alternating, so these two informations that we have. Therefore, now you look at the following. Define A tilde by let us define a new form on R3, new three linear form on R3, namely A tilde, and A tilde is defined through A using the linear transformation, the given linear transformation A. Now this is well defined. Okay. Now you can easily see that A tilde is three linear. That means linear in each of the arguments when the other two are held fixed. That is easy to see because the linearity of A matters in this computations. Further, A tilde is an alternating Now that's very easy to prove because if you interchange x1 and x2, what happens? You have to interchange x1 and x2 here. When you interchange x1 and x2, you are interchanging ax1 and ax2. So the sign changes, and then from there you can actually prove that A tilde, you can actually verify that A tilde xi, xj, xk equal to minus of and etc. That means when you interchange any two of the, if two of the arguments are identical, then A tilde is 0. If you interchange any pair of arguments, then the sign changes. Now this can be easily verified because it comes from the corresponding property of A of AX1, AX2 of A with arguments as AX1, AX2, AX3. You can easily verify this. Okay. So A tilde is an alternating three linear form. Therefore, you see that A tilde is essentially a scalar multiple of A. Okay. We shall explore what constant, what scalar multiple, what this scalar multiple turns out to be. So our problem is this. What is this K? We shall now determine what this K is. But we know the following. We know that A is equal to sum this is a scalar multiplied by what is called E1 E2 minus so this is what you have. A is actually this. Okay. Now we shall use this formula and or this property of the relationship between A and A tilde, and then try to find out what this constant turns out to be. So the question is, what is this constant K or scalar K? How is it related to? This is the question that you ask. Can you write it explicitly in terms of A? where A we have already seen the what you call the in terms of E1 E2 yeah exactly. So we have seen A is written in this term, so now it is quite easy to work it out. Okay. Now let us explore this. To explore this, structurally everything is clear. All that is, we are searching for what it is, what this scalar is. So it is enough to verify what happens at, so you can compute K if you can compute A tilde E1 E2 E3 and A E1 E2 E3. Okay, so let us work it out. So you know that A is completely determined if we specify what is A E1, A E2 and A E3, because A is linear on R3, E1, E2, E3 forms a basis for R3. So we shall make use of that. Okay. So let me just work on that. Note that, so we will compute A E1. A E1 is equal to A11 E1 plus A21 E1 E2 plus A31 E3. A E2 equal to A12 A22 E2 plus A E3. So also A E3 equal to, this is quite easy to work out once we assume we are given Aij. A13 23 E2 plus A33 Now calculate A tilde E1, E2, E3. So A tilde E3 is by definition, this is equal to A E3. Now this you can write as A evaluated at I can write this way, in this form, sigma AI1 EI, I running from 1 to 3, sigma I running from 1 to 3, AI2 EI, sigma A I3. So this is what it is. Now what we know is that A is what? A is alternating and it is a 3 linear form. Therefore, it is linear in each of the arguments when the other 2 are held fixed. So we make use of that. So therefore, what we end up with is this. Yeah. Let me write down the computation. Therefore, if you work this out, what turns out to be is this. Okay. This is equal to summation, let us use that. So, AI running from 1 to 3 J running from 1 to 3, K running from 1 to 3. I am just using the linearity with respect to each of the arguments. So, if I were to do that, then I get AI1 AI1 AJ2 AK3 AK3 of A of EI EJ EK. Okay. So, you got all the terms coming out from this, right? Out of which now you look at this term. So, look at the expression for A. A is of the form A E1 E2 E3 multiplied by all these numbers. Okay. Therefore, if you write it out, it will turn out to be, and you see, when you have E1 E2 E3, it is equal to 1 only on when it operates on E1 E2 E3. Okay, right, and so on. Therefore, if you make use of that, see, you make use of that, then what you get? So, this is what you end up with. This is equal to, substitute that expression for A and using the definition of Ek. This is just a matter of putting it and then evaluating it here. Okay, because instead of A, you have to write this multiplied by this one. Then you see you are having all sorts of things, 1, 1, 1, 1, 1, 2, and so all sorts of combinations are there, and you have to use the fact of A being alternating, which will make if any two pairs of this are 0, then this is true. So this sum actually reduces at the outset. Okay, at the outset itself this sum reduces. This sum reduces to, you see that several terms of this become 0. That means whenever any pairs of this are equal, it will go to 0. For instance, when you take I equal to 1, j equal to 1, k equal to 1, a of E1 is 0. Okay, or a of E1, E3 is 0, and so on. So if any two pairs are equal, then this becomes 0. So you are left with a sum involving I, j, k, right, with appropriate signs, I not equal to j, j not equal to k, and I not equal to k. They cannot be equal. Therefore, this will reduce to what is called A12, A23, 31, then plus A13, A21, A32, minus A13, A13, A3, A23, A31. This is what it is. Multiplied by AE1, E2, E3. Okay. And therefore, what you get? This you can easily see that this is equal to A11 into determinant of A22, A23 A32 A minus into A21 A23 A33 plus, you see that the common factor here is A13, so A13 into determinant of 2 by 2 determinant of A21 A21 A22 This is A22, okay. A13, A21, A32, correct. So A13, A21 into A So A21 A32 minus A31 A22, right. This multiplied by okay, and if you observe what exactly is it, this is equal to determinant of A. You can check the entries there. There could be some slip. It's quite possible. I don't vouch for everything. So this you can show that this is actually equal to this is what you get. Okay, therefore this is equal to determinant of A multiplied by A whereas this you know is essentially A of okay, therefore you get A tilde is equal to this, therefore this is the final result. Hence So that's the theory. Okay. So you see that the determinant comes up as the scalar multiple when you look for the relation between A tilde and A, both are alternating 3 linear forms. So with this, now we are in a position to explore the general case. All that you need is just get the notations right, and then you will see that everything emerges. Now you got an idea what exactly you want to do. So what you do is, the systematic procedure is that you explore the, in this case, the space of all 3 linear forms on R3. Show that it is a vector space of dimension 3 to the power 3. Then you take up the, you actually construct a basis for that. Then you take up all 3 linear alternating, all alternating 3 linear forms on R3. You observe that it forms a subspace of the space of all 3 linear forms on R3, and then you explore the dimension of that, and in fact it turns out to be of dimension 1, and then you can construct a basis for that. So every element of that becomes a scalar multiple of this particular, the vector you have identified, or the n linear or the 3 linear alternating form on R3 that you have identified, which is a very interesting expression. Now you explore the following. Define A tilde xi, xj, xk as by A of AXI, AXJ, AXK, where A is a linear transformation, is a fixed linear transformation on R3. Then we can actually compute what it is, because you know that A tilde is again a 3 linear alternating, an alternating 3 linear form on R3. Therefore, A tilde has to be a scalar multiple of A, right? And what is that scalar? That scalar turns out to be exactly the determinant of A. So determinant of A is something intrinsic to the linear transformation A, okay, and that comes up naturally in this connection, and that is what we have explored. So determinant of A is not a freak definition that you make to suit some purposes, but it's a beautiful scalar valued function that you define on square matrices with some remarkable properties. Thank you very much.